Today we're going to be talking all about drivetrains, specifically mecanum-based wheel drivetrains, and what factors make a mecanum wheel drive good, what makes a mecanum wheel drive bad, and how can you design or make sure your drivetrain doesn't fall into these pitfalls that a lot of people end up designing when they're making their robots. Now, I've been teaching robotics for over a decade now, and I've seen a lot of problems that come up with chassis and drivetrain designs that just aren't really up to snuff. And particularly in the world of mobile robotics, if your drivetrain is not solid and it doesn't have good design principles and foundation set up behind it, you're really asking for trouble with the rest of your robot all the way down. Now, in my opinion, the most important thing on a drivetrain itself, maybe not necessarily the side plates that are protecting these things, but the drivetrain itself is a rigid system. When I talk about drivetrain, what I'm really talking about here is I'm talking about the parts that actually move the robot. So the wheels themselves, the motors themselves, any sort of belt pulleys you have that are able to transfer those motors across, and any sort of substructures that are connecting these motors together. Now, one of the most important things here is you don't want to be able to have what's called a lot of racking. So if I were to take this and I were to move it on an angle here, you don't want to be able to have a lot of twist and flex on your design. Now, I've got a lot of flex up in the top on this design here because there's nothing adding any sort of braces or supports across this. But if I were to try to flex this thing sideways and I try to break and move this thing sideways like this, it's actually fairly rigid. If I want to get a little more rigid, I would consider adding in some sort of triangles here, because down here where I've got this sort of brace support, as I add in this flex here, I don't have a lot of racking force, but when I come up here, watch what happens. See how I can get a lot more flex up on the top of there? That could really easily be reduced just by adding in a large cross brace down below, and we have that racking. So based off this design, this bottom part definitely passed the rigidity test. This top part does not pass that rigidity test because we can rack that top bit quite a bit. But again, adding in some sort of triangle support there would significantly reduce that. Another important factor on your wheels is you can have a cantilevered system versus a non-cantilevered system. So when I'm talking about a cantilevered system here, that means typically you've got your wheel here, it's supported on a single axle, and it's not supported on the other side. The problem with a cantilevered system is that your wheels are going to face a lot more deflection, a lot more force on that, and you need a lot more support on a cantilevered system than you do. That's where I like parallel plate designs, in that you have an axle shaft that is running directly through. It's supported on this side and on this side, and then that force transfer from the motor is coming from a pulley. And that makes your life a lot easier to be able to get more consistent force transfer across that as well. Now, you do have something here where you've got an integrated motor design, where this does initially look like a cantilever design, but it's mounted on this side and secured on this side, and the motor is actually baked inside of this wheel here. So this is actually not a cantilever wheel system. It's also quite a small little system set up on that drivetrain. Another thing that I prioritize highly in my drivetrains is to be able to have modularity or support on these things. I really like designing with grid plates patterns on these things. So whether you're using aluminum extrusion for a slot or channel-based system, whether you're using channel from something like Swift or GoBuilda or Rev Robotics, being able to add in additional points up on the top of your drivetrains that you don't have to take the whole thing apart when you want to mount more mechanisms, more electronics, more sensors, whatever have you, really makes life a lot simpler. So being able to add in lots of mounting points around these drivetrains really does, in my opinion, perform and make your drivetrain a lot simpler to prototype on. Because if you were to take this whole part off and you're just left with this bottom section, you don't really have easy mounting points to be able to change your design over time if you want to. Another thing to consider when you're designing a mecanum drivetrain is the wheel circumference or wheel diameter as well. Really common one on the market right now is a GoBuilda wheel here. Their old system used to be 94 millimeters. They also got 104 millimeter as well, but there's also 3 millimeter diameters. Things like the 77 millimeter from AndyMark here, or the 75 millimeter from Rev Robotics here. Now, why might you consider using a larger wheel, or why might you consider using a smaller wheel? Now, a larger wheel versus a smaller wheel is kind of like an external gear ratio that you're adding in. The larger your wheel you have, the less gear ratio you need to be able to get a higher ground speed. To be able to achieve the same ground speed as a larger diameter wheel, a smaller diameter wheel does have to move quite a bit faster. In fact, because this one has about 104 millimeters, this one's about 75 millimeters, this one's going to have to rotate about 25% faster than this one is to be able to achieve the same ground speed. But on the flip side, because this one doesn't require as much torque to get up and running from your motor, you are going to be able to accelerate a lot quicker with a smaller wheel than you will with a larger wheel. The same goes with braking. A larger wheel is, of course, going to have more rotational inertia as it spins around. It's going to require more force to be able to slow itself down than a smaller wheel will. So some of those directional changes are going to feel a little bit heavier on a larger wheel than it will on a smaller wheel. You can also think about total packaging. This is 104 millimeters. This is 75 millimeters. That's almost a 30 millimeter difference. And that can make a huge difference in packaging. When you look at this design here, look how much extra space you've got between your wheels compared to if I were to put in a full 104 millimeter design there. You significantly reduce the amount of space that you have inside of some sort of parallel pod plate design, which makes it a little bit harder for you to be able to fit things like odometry pods or other control systems in between your wheelbase. But on the same side, your rolling resistance is lower on a larger diameter wheel than it is on a smaller diameter wheel. So it's a little easier to keep this thing moving than it is to keep a smaller wheel moving. As well, a larger wheel is going to tend to absorb shock a little better than a smaller wheel will, as well as be able to control itself up and over objects as well. Because you've got a larger wheel, you have more of that surface area. You tend to have more of these wheels in contact with the ground than you do with rollers on another smaller wheel system. So depending on where your motor curves end up choosing, what you are driving this with motor curves wise, depending on how fast or how slow you're going to be moving these things, that does actually change up your design quite a bit. Now, another thing to consider when it comes to designing drivetrains is things like electrostatic discharge. And that is a big problem when it comes to full aluminum chassis like this. Because this robot here, if it were to collide with external factors, depending on how good the electrostatic protection is on your control hub systems, as you run into things around the environment that have different levels of static charge, you can actually end up causing some disconnections from your robot controller to your drive system to your robot, depending on how those electrostatic discharge events actually end up occurring on your robot. Something like a plastic chassis on the outside, like acetal or polycarbonate, or even a vinyl wrapped aluminum, doesn't end up running into that same problem because you don't, when you collide with another robot, or you collide with the field perimeter, or you collide with another implement that your robot is going to interact with, you're less likely to face some of those electrostatic disconnects than you will over here, particularly because mechanism wheel drives driving around on carpet have a real bad habit of driving and picking up static electricity like crazy. Another thing to consider is the total weight of your system. How thick materials you have really does end up making a big difference. A lot of people will do things that do some lightning patterns. So for instance, you see on this drivetrain here, it's got all these little hexagon shapes to be able to reduce some of the weight on the system without reducing some of the rigidity on that. As well, same thing over here on these more channel-based systems. You do have a lot of holes along them that not only help with modularity to add things in, but it does mean that you're also making your robot a little bit lighter. And depending on what you're doing with your robot, whether it's going to be pushing, you probably want a heavier robot. If it's going to be driving around, has to do things quickly on its mobile, you probably want a much lighter robot that's going to perform better. And sometimes by being able to take some weight off of that drivetrain, it allows you to add more weight in other areas where it really matters. Now, a note on the weight, it's really important on a mechanism chassis that that weight is evenly aligned across your robot, because if it's not evenly aligned, what can end up happening is your strafing will be in strange performance and driving forward will also be in slightly strange performance. You're going to end up drifting over to one side, or instead of driving perfectly straight, you might drive in a bit of a crescent shape instead if you have slightly different friction across your wheels, or you have a different weight balance orientation on your robot. If you have too many bolts, too many things that are hard to reach, you can't get your fingers up and inside of your chassis, you can't get a tool inside of there, you can't reach where critical components are, it ends up meaning that any sort of repairs you need to do on the fly really reduce the amount of time you have to do that, and means you're having to take whole plates off, having to take off parts. You really don't want to have to disassemble your robot to be able to fix it. So being able to add in things like maintenance holes, clearance holes, and so on, just to be able to get tools through on things, I think is a really important design. And the last thing that's really critical on a drivetrain itself is, of course, the ease of manufacturing. Making things like this robot here does require a lot more custom parts. You need to be able to cut things down. You need to have the tools to be able to do perhaps a laser cut or a water jet or a CNC, depending on where it is. That's where channel-based systems become a lot more attractive, because you might already have parts that already fit with the Rev Robotics system. You might already have parts that fit with the GoBuilda system. And being able to have those parts that fit in, be able to just cut them down and slap together really is a huge boon. When we talk about the performance benefit of having something that is completely custom versus non-completely custom, there is that drawback to consider, that if you're going to go a completely custom route, you really need to consider, just do I have those manufacturing capabilities to be able to do that custom route, and do you have the budget to be able to do that fully custom route as well? Because a well-built drivetrain with a custom chassis, in my opinion, is going to outperform a poorly built, custom-built drivetrain any day of the week, particularly if you are focusing on what other things your robot needs to be focusing on instead of just the drivetrain chassis itself. So there's a lot to think about when it comes to doing Mecanum drivetrains. If I had to pick a couple of things that are most critical and important, first one I focus on is budget. Do I have the tools? Do I have the ability to be able to make something like this? If I had to favor one, I tend to favor for more experienced builders, making something that's a little more custom, making something that is more of a parallel pod design. You can add in any sort of components. You can add in that modularity as you want to. That does make some of those channel-based systems a little bit more restrictive. If you're on new at the beginner side of things, I tend to favor being more on the channel-based system here, just because it makes it so much easier for us to be able to add things and take things off as things are needed. And as we move things around, particularly in those early design phases, having that ability to have those modular holes so you can just add components, add sub-assemblies wherever you want, it does make your life so much easier on those initial prototyping phases. As you get your robot towards those further and further prototypes, more towards your final designs, then you can start cutting out some of these more modular designs. And there's some more channel-based systems in here to be able to get more favor of more complex materials and a little more advanced usage in your robots. And the last thing I'll say on drivetrain is rigidity is absolutely critical to be able to have that. You really don't want to have any racking across, being able to take those squares and rotate them diamond wise. If your drivetrain isn't rigid, it's kind of like trying to shoot a cannon off of a canoe. You just don't have a stable platform to be able to drive around on. And that's really where some of those benefits of those channel-based systems come in, because they end up being a lot blockier, they end up being a lot thicker. It's a lot easier to make these things rigid than it is to spend the time making a fully custom design. If you'd like to build either of these robots, I've got the full CAD for them in the community down below. I've also got a full tutorial on how you might be able to design out one of these drivetrains fully step-by-step in Fusion as well. I'm curious what your kind of top 3 criteria are based off of that. You know what mine are. Let me know in the comments below where yours are. If you got any questions, let me know in the comments below. And as always, best of luck on your next robotics project.